Hello, hello. This is going to be a video walkthrough of problem 2 on CS61B Spring 2021 exam prep worksheet number 7 covering asymptotics and ADTs. So this problem is very difficult. So if you guys saw it and didn't know where to start, that's perfectly normal. And I'll give you guys some intuition on how you guys can approach this problem and other similar problems in the future. Okay, so suppose that we have the flip function as defined below. Assume the method unknown returns a random integer between 1 and n, exclusive, and runs in constant time. For each definition of the flop method below, right, this is the flop method, we are trying to figure out the best and worst case runtime of flip in theta notation as a function of n. Okay, so just to reiterate what's happening here is that we're trying to figure out the runtime of flip, and we're considering the runtime of flip for different definitions of this flop function. Okay, and what is happening is that flip kind of calls flop, and then flop recursively calls flip. So it kind of like flip flops back and forth, hence the name of the problem. Okay, anywho, so diving into part A, we have this flop method where it takes in an int I and it takes an n and it calls flip of n minus I. Okay. And before I get into the runtime of part A, I want to tell you guys one quick thing is that looking at the code that's given, we see that we have this base case here. If n is less than or equal to 100, I'm going to argue, just to make like my life easier in the future, that this is the exact same asymptotically as n is less than or equal to 0, or any constant for that matter. Okay, so if you guys aren't really proven, like if you guys don't really think this is the case, I made a quick walkthrough video on misconceptions and confusions that should be linked second in this playlist. So recommend watching that. But let's change this to 0. And the next thing I want to try to figure out about this function before diving into part A is that when we look at this stop, we will notice that no matter the value of stop, at some point in this for loop, we have to hit this if condition. Okay, so this if condition will be true for some I. Okay, and what that means is that every time we call flip, if we don't go in this base case, we will always call flop and then return. Okay, just good to like understand that before we dive into these parts. Finally, without further ado, diving into part A, we will see that we have flop, which calls flip on n minus I. Okay, and this one is actually a really tricky part. You guys could kind of guess on intuition, but I'm going to walk through a process that rigorously shows you guys the answer. But for this problem, I'm actually just going to tell you guys the answer and then prove why it's the case. So the best case and worst case runtime of flop is going to be theta of n. Okay, and you guys might be wondering, like, how did you figure that out? Well, I'm going to show you guys right now. But what's important to notice is that if the best case and worst case are the same, it implies that this function always takes n time. Okay, that's a very important thing to realize if when the best and worst case are the same. So looking at the first call to flip, it'll be of input size n. Okay, now there's many possible recursive calls we can do, right? Because I could equal stop from any value from 1 to n minus 1, right? So there's so many things to consider, it's kind of confusing. So we're going to have to like slightly nuance our tree diagram a bit, okay? So what I'm going to do, I'm going to draw a couple nodes. Let's draw. Let me move them over a bit. Okay. So And I'm saying this is 0 to make life easier. Okay, looking at this little diagram I made, let's realize that when we're at this top node n, there's many possibilities for what we can do. We can go straight to n minus 1, right? This is the case when stop is equal to 1, in which case the first time we enter this for loop, I is equal to stop, and we immediately call flip of n minus 1, right? That's the case at this node, okay? The next case we can consider is, let's consider an arbitrary I, right? This is just saying, like, we know that at some point I will be equal to stop, and we will call flip of n minus I. So we'll consider that n minus I case, okay? And then the last possibility, where I just kind of put at the bottom here, is like, what if we go all the way to the end immediately, right? So these are all of like the possible cases. I'm going to say this is like 1, just to we can actually get there, okay? So looking at these possible cases, we can kind of see that if I choose this case, it'll be a different amount of work in the scope of the flip function as if I chose this case, right? Because if we're going to the n minus 1 case, we're only doing one work in flip the first time around. If we're going to this possibility, then we're actually doing I work, okay? So since the amount of work that we do in flip varies based on which recursive call we intend to take, I'm going to have to slightly change our drawing, where instead of having the work inside of the node, I'm going to attach the work with each arrow, okay? So we will say the work will be in red, okay? And we can see that going from n to n minus 1, that will take 1 work. Okay, that was a terrible one. It'll take 1 work. That's still a bad one. 1 work. Okay, going from n to n minus I, this one's very important. It takes I work. The reason we use I work when we're going from n to n minus I is because we have to have executed I steps in this for loop prior to calling flip of n minus I. Okay, so we can kind of see that we take I work to get to this n minus I node. And then if we're going all the way to the bottom, it means we did n minus 1 work. Okay, and now this is a very, very important realization to make, is that if we kind of divide up this tree into levels, okay, so in this case, this is like level 0, level 1, level, it's kind of in reverse order, my bad. Okay, but if we're looking at each level, in order for us to go from one level to the next level, my claim is we will always do 1 work, okay? And you guys can kind of look at this drawing and it'll prove to you guys why this is the case. That whenever we go from one level down to the next level, it'll always be 1 work, right? When we're going from level 0 to level I, we're doing I work, right? So moving down 1 level always will take us 1 work, no matter what recursive call we do. So finally, summing up this problem, if we look at all possible ways to get from this top to this bottom, we look at all possible paths, right? There's so many different ways of getting there. We look at all of these paths, we will see they will all be of total weight n, right? What I'm saying is that the total amount of work that we do along all of these paths is always going to be n work. Because we have this idea that as we move from one level down to this next level of the tree, it's not really a tree this time, but regardless, we always do 1 work to move down 1 level, which means looking at all possible ways of going from this top to the bottom, all of these paths have total work n, which gives us best and worst case n. Okay, hopefully this made sense. Definitely a very tough question, but moving on to the next one now. Okay, so moving on to this next possibility. Now we have a call to flop where we have the minimum, which is the minimum of I and n minus I, and then we issue two calls, the flip of the minimum and another flip of the minimum. Okay, so in this case, it's actually pretty tricky of where to start, right? It's like kind of confusing. Where do I even go from here? So what I'm going to say is that let's start off with this best case possibility. Intuitively, when we think about the best case, how we want to approach that is we want to figure out, that was not a great arrow, what will take the least amount of time possible. Okay, so when we consider best case, we're trying to exit our function as quickly as possible, right? So in order to exit as quickly as possible, let's explore the possibility where stop is equal to 1. Okay, let's draw that possibility out. What will happen in that case is we will first call flip of n, right? Then we will see that stop is equal to 1. So the first time we enter this for loop, this if condition is true, and we immediately call flop of 1 and n, right? Calling flop of 1 and n will set the minimum equal to 1, which will issue two calls of flip of 1, okay? So looking at that first call to flip, we see that we're doing one work and we issue two calls, right? Where we do flip of 1, okay? And then we can kind of see that both of these calls hit our base case, right? So in that case, they terminate immediately and they do constant amount of work. So we can kind of see here that in this possibility, we're doing a constant amount of work, right? When stop is equal to 1 the first time around. So that actually produces our best case behavior, since you can never do better than constant time, and we've produced a situation that runs in constant time, we can say the best case is theta of 1. Okay, let's look at another possibility, and that's worst case. And when we explore worst case, we're trying to answer the question of what will take the most amount of time possible. That's the question we're trying to ask ourselves when we explore this worst case possibility. So looking at this function here, how in the world are we trying to like figure out what takes the most amount of time possible? So my idea is there's two ways that we can kind of think about what takes the most amount of time possible. Idea one, oh, I don't know why that appeared. Okay, sorry about that. The first idea to try to consider cases that take the most amount of time possible is what if this for loop goes all the way to the end? Okay, I'm just kind of like thinking out loud, and as you guys approach problems, you guys probably will do the same. So if this for loop goes all the way to the end, we will call flop of n minus 1 and n. You guys see that? Because if it goes all the way to the end, we know stop is some number between 1 and n minus 1, right? So in that case, stop is at the very end, stop is n minus 1. And what we will notice in this case is that the minimum, when these two numbers are passed as input, is going to be 1. So despite executing around n work for that first call to flip, we still produce two calls that terminate immediately. Okay, so we've thought of a situation that takes n time, but my question to you guys is there a possibility where we can possibly do more than n time? And there indeed is. And how we can stumble upon that is noticing that in this possibility, the reason that we stopped doing work is because the minimum was too low, right? 1 is too small of a minimum. So my idea here is, in order to consider what will take the most amount of time possible, let's try to think about the case where minimum is as big as possible. This is my next idea. So if minimum is as big as possible, it means that when we call our function recursively, the input size is as big as possible, right? And intuitively, I think that kind of makes sense, that whenever we call our function with a bigger input, it kind of produces more work, right? And that's what we're trying to consider here. What possibilities will take the most amount of work? So to make the minimum as big as possible between I and n minus I is setting I equal to n over 2. Because if I is equal to n over 2, then the minimum of n over 2 and n minus n over 2 is basically n over 2, right? So what we can say here is, now let's consider the possibility where, oh man, I did not mean to do that. Now let's consider the possibility where stop is always equal to n over 2. Okay, so stop will always equal n over 2. In that case, let's look at this corresponding tree that develops. We will see the first time we call this function, I'm going to get rid of some of this just for the sake of space. The first time we call our function, we will have an input size of n. And the total amount of work we're doing in this function call the first time around is n over 2 steps. Okay, we're doing n over 2 work the first time we call flip if stop is equal to n over 2. The reason we do n over 2 work is because we have to execute n over 2 steps of this for loop, right? Okay, so with that in mind, let's think about the two recursive calls that will happen when we call flop of n over 2 and n, right? I kind of touched on this before, but what will happen is we will call flip of n over 2 and n over 2, right? And how that looks in this corresponding tree is we will call flip of n over 2 and flip of n over 2. Okay, now let's explore another iteration of this process where stop is always n over 2, which means we always stop halfway in the for loop. Okay, and what we'll realize is that we'll kind of get something that looks like the following. Okay, like the next level of the tree, we will have n over 4, n over 4, and then I can duplicate this for this side. Okay, so this is kind of this tree that we see happen. And how much work are we doing at these nodes? Well, looking at the nodes on this level, we're always doing n over 2 work. So if n is equal to n over 2, this means we're doing n over 4 work here. Then the next level, we're doing n over 8 work. Okay, so the final thing we want to do here is whenever we approach these types of problems, we want to figure out the work per level. Okay, so looking at the work per level, let's move that over here actually. Looking at this top level, we're doing n over 2 work. Looking at this next level, we're doing n over 4 plus n over 4, which is also n over 2. Looking at this next level, we're also doing n over 2 work because the sum of n plus 8 plus n plus 8 plus n plus 8 plus n over 8, okay, is n over 2. So to try to figure out the total runtime of this function, we need to figure out the total value of this sum, right? And if we look at the sum, it's n over 2 plus n over 2 plus n over 2. And how many of these n over 2s are in this sum? Log base 2 of n, because that's the height of this tree. Height log of n. Okay, so the total runtime here is going to be, I'm going to get rid of some of the stuff just for legibility sake. The total runtime is going to be n over 2 times log base 2 of n. And then when we think about asymptotics, we don't really care about the base, and we ignore these constants or coefficients. So we see the worst case is n log n. Wow, that was a tough problem. Okay, We're almost there. One last problem. So looking at this last problem, it's definitely very tough. I mean, all of the problems in question 2 are really tough. So no worries if you guys got a little stuck here. But, okay, let's go for it. So this last case, we have flop of I and n, okay? And we're considering, we can call flip of I and flip of n minus I, okay? Let's explore the best case possibility first. So when we think about best case, we're trying to figure out what will take the least amount of work possible, okay? In the first gut instinct I have, my intuition tells me let's try to exit this for loop as quickly as possible, okay? Which in other words is saying, let's set stop always equal to 1, which means that we always exit this for loop on the first time we enter, right? And what we will see is that we kind of get this corresponding tree, where the first time we call flip, we do one work, and then we issue 2 recursive calls. We issue a recursive call to 1 and a recursive call to n minus 1. So how that's going to look is that we have 2 calls. We have one call to n minus 1, and we have another call to 1, okay? And then also notice that each recursive call, or each time we call flip, we will always be doing constant amount of work, okay? Because we exit the for loop immediately. And what we will see happen is that this recursive call basically just terminates immediately, right? Because we're passing in input size of 1, which means we're at the base case. So let's keep exploring this possibility of every time we call flip, let's always have stop equal to 1, which means we kind of produce this corresponding tree, okay? And what we will notice is that this tree kind of continues. Where we kind of have like this tree where at the bottom we have like 1, 1, right? So to try to figure out the total amount of work of this tree, we can kind of see here that at each level, we're really just doing 2 work, right? Except for the top level. So it's like 1 plus 2 plus 2 plus 2 at the bottom level, okay? And you guys can kind of see that the height of this tree is n. So the total amount of work we're doing is roughly 2n, but basically just n. So this is the best case possibility, and I'm going to quickly prove to you guys why this is the best case possibility. And the proof is actually, like, I think, rather slick. What I'm going to say is, looking at this definition of flop and looking at this definition of flop, the only difference is that we have one more recursive call here, right? And a recursive call can only add to the runtime of a function. So in this possibility, if the best case is theta of n, and we're considering this definition of flop with one more recursive call, we know that if we have a situation that takes n time, we can safely say that that indeed is the best case because we can't do better than n, right? The reason we can't do better than n is because if we're looking at the same flop definition without one of the recursive calls, in this case, it still takes n time, right? So what we know that this indeed is the best case, okay? We're almost there. Okay, you guys have made it. The last possibility is the worst case. So when we're considering this worst case possibility, what I'm going to do is I'm going to divide, or I'm thinking of the possibility that takes the most amount of time possible, okay? When we're looking at this possibility, my idea here is let's do as many steps in this for loop as possible. In other words, let's set stop equal to n minus 1, okay? Okay, I need a quick sip of water. I'll be back. Okay, I am hydrated and back. So considering the worst case possibility, my idea is let's exit this for loop at the very end. Okay, what that's saying is we're setting stop equal to n minus 1. In this case, we will actually get the same exact tree in terms of structure. The only difference now is the work per node is different. Let me elaborate. So if we set stop equal to n minus 1, it means that we have executed around n minus 1 steps in this for loop. I'm just saying that we're doing around n work, okay? And then what we're going to do is we're going to call flop over here with n minus 1 comma n, okay? Which issues two recursive calls. We have a recursive call to n minus 1 and another recursive call to n minus n minus 1 or 1. You guys can hopefully see that. And what we will see is that we're still doing the same recursive calls as the best case possibility. The only difference now is that the amount of work that we're doing in flip has increased from constant to n. Okay? So what we will see is that the tree will look very, very similar, exactly the same in terms of structure, but now we're doing n work for that first time we call flip, because we have to iterate all the way to the end of the for loop. And the next time we're doing n minus 1 work, right? This one is just constant amount of work because it's still the base case possibility. But now what we can see is that we have a little more work at each level of this tree, right? So to find the total amount of work that we're doing in this case, we can simply look at the work per level. And what we will notice is that we have n work at the top, then n minus 1, roughly n minus 1, and then roughly n minus 2, all the way down to 1. And we can see that we get the sum of n plus n minus 1 plus n minus 2 plus 1. And we know that this sum is just the reverse of the sum that we love, which is on the order of n squared, right? Asymptotically. So what I've shown you guys is a possibility that takes n squared time. Now I'm going to argue that this is indeed the worst case possibility, okay? My argument is as follows. Let's suppose that we're exploring the possibility where we have the first call to n, and then we have two more recursive calls, okay? So we have a recursive call where the size is I, and then we have another recursive call where the size is n minus I. Okay, I'm just exploring an arbitrary possibility. And I'm going to show you guys that even in like this arbitrary possibility, we can never do more than n squared work. That's my idea here. I want to prove to you guys that n squared is the most amount of work we can ever possibly do. Okay, so if we're exploring this possibility, what we will notice is that if we look at each level of the tree for any possibility, we will always see that we're doing n work at each level. In the worst case, like we can never do more than n work. The reason we can never do n work per level is because each node, each time we call flip, the most amount of work we can do for one function called a flip is n work, right? We can never do more than linear work in flip, right? Which means that each level of this corresponding tree will always be doing at most n work, okay? So if each level can do at most n work, and the most amount of levels this tree can possibly have is n levels, right? This is saying that the maximum height of this tree is n. So if the maximum height of this tree is n, and the most amount of work we could possibly do on any level is also n, the most amount of work that could ever possibly happen is n squared. And since we've now shown a case that runs in n squared, we know that this is indeed the worst case. Okay, so that is all for this discussion walkthrough. I congratulate you guys for staying to the very end. I know it was long, and yeah, hopefully this made sense.